we'll continue on here. What I did in my talk. All right, so I just, during the break, I was approached with a few questions. I just want to clear up any anything that might be confusing you. When you look in the table and you look up a z-score, okay, you are looking up a z-score, and that will always, the table always tells you the area to the left of the z-score, okay? So if you look up z equal to negative 1.0, what the table is giving you is the area to the left of negative 1. Okay, so always 0 is in the middle. We're looking up z equal to negative 1, and you'll get something like 0.1587. That is the area to the left of negative 1. Okay, it's not anything else. You are always looking up, when you look it up in the table, you're always getting the area to the left. Okay. The reason why in some problems I subtract the area I find in the table from 1 is because that problem is asking for the area to the right. Okay. So if the problem asks for the area to the right, then I would take the area to the left and subtract that from 1, because the total area under the curve is always 1. So if the problem asks what percentage of giraffes are heavier than some amount, okay, or taller, or bigger, or is greater than, or something. Whenever your question asks, is more than, any of those types of words, it's probably asking for the area to the right. Okay, so in that case, you would still look up your number in the table. The table always gives you the area to the left, and if you want the area to the right, you subtract that number from 1. Okay. One thing I also noticed when people are doing their work, it's important to distinguish your z-score from the area. Okay? Don't write, so this is if you can keep track of everything, it's okay, but this is bad practice, is to say z is equal to 0.83 and say that is equal to 0.7967, okay? That is not the case, okay? There's no universe or no set of math where 0.83 is equal to this number, okay? It is that z is equal to 0.83, and that corresponds to an area of 0.7967, okay? So don't say that 0.83 equals 0.7967. You could draw an arrow, okay? That's fine. But z is equal to this, your z-score, the number of standard deviations you are from the mean is equal to this number, and that corresponds to an area, and I always say area L or area R or whatever, depending on what I'm doing, just so I can keep track myself. So I say the area to the left is 0.7967, okay? And that way, you'll avoid confusing yourself. I hope that clears up any issues here, okay? Always, when you calculate your z-score, it's always your value that you have minus the mean, minus mu, divided by the standard deviation, okay? So the mu you're always taking y minus mu. Don't flip those around, otherwise you'll get the wrong sign, okay? So if your value is below the mean, your z-score should be negative. If your value is above the mean, your z-score will be positive, okay? So if you mix up the signs, if you did 1600 minus 1500, you would get the wrong sign, okay? And then you'll just confuse yourself, or maybe not, maybe you'll sort things out. Sometimes on tests, I see people make, one mistake, and then they make another mistake which happens to cancel out the other, their first mistake, and they get the right answer. And so I feel bad taking off points, but don't count on making future mistakes that will cancel out your past mistakes. That's generally not a good strategy here. Okay. All right, so we were able to use the z-table to look up the area, or the percentage, if if we're given a measurement. In your textbook, you'll have a few homework problems, and they phrase the questions a little differently. Okay. Well, they might say, what percentage of giraffes weigh less than 1,500 pounds? Okay. They could also change the question, but it's asking the same thing. It just sounds a little different. They could say, if we selected a giraffe at random, what is the probability that this randomly selected giraffe weighs less than 1,500 kilos, okay, or kilograms? Both questions are asking the same thing, okay? The percentage or proportion of giraffes that weigh less than 1,500 kilos is the same as the answer to the question, if we select a giraffe at random, what's the probability that it's less than 1,500? So don't let that change of wording confuse you. So that is, that's giraffes. We also have the, not giraffes, that's z-scores on the table. We have the reverse reading of the table as well, okay? So I could say, what z-score corresponds to the 40th percentile? So, well, maybe we need to take a moment and just ask, well, what does it mean to be in the 40th percentile? Or what does the 40th percentile mean? Yeah, so it is the point, the 40th percentile is the point where 40% of the data, or 40% of the population, is smaller than this point, okay? So if your weight is in the 40th percentile, that means 40% of people weigh less than you. And conversely, that means 60% of people weigh more than you. If your intelligence is in the 80th percentile, that means 80% of people have lower intelligence than you, and 20% have higher intelligence. However, we were to measure intelligence, if that were, if we had some way to do that, okay? So we could ask, what is the z-score that corresponds to the 40th percentile? Okay. Well, before we even try to answer this, is this z-score going to be positive or negative? Negative, right? Because the 50th percentile corresponds to a z-score of 0, okay? And if we are above the mean, we have a percentile that's higher than 50th percentile, higher than the 50th, I should say. And if we have a z-score that's negative, we would have a percentile that's lower than 50. So if I were to draw my normal curve, the mean is right here at 0. And what I'm asking for is I'm asking, what is the z-score that goes right here so that the area over here is equal to 40%? Okay. Well, can you look in your table and figure this out? So what you will find is that you will not find 40%. Okay, so what you are looking for is you're looking for a number close to 0.40. Okay, but you won't find exactly 0.40. You will find 0.4013 and 0.3974. Okay, this is on the negative side of your table. You will find 0.3974 and 0.4013. 0.4013 corresponds to a z-score of negative 0.25, and 0.3974 corresponds to negative 0.26. Okay? So we're faced with a choice, and we have to choose one of these numbers. Okay? I just say go with the one that's closer to the one that you're looking for. So in that case, we would choose what? Yeah, z equal to negative 0.25. Okay, this is 13 10,000ths away, and this is 26 10,000ths away. 0.0013 versus 0.0026. So we would say z is equal to negative 0.25. You don't have to interpolate and say z is equal to negative 0.25 or 253 or something like that. Well, that would probably be the closest to the truth. All right. Is that okay? Getting the z-score based on a percentile. All right, so if we say what z-score corresponds to the 40th percentile, what could I say? Can I ask, what is the weight of a giraffe, of a male giraffe in the 40th percentile? Well, in answering this, your first step, step 1 is find the z-score that corresponds to the 40th percentile. And we've already done that. We found that z is equal to negative 0.25. Okay, so if z is equal to negative 0.25, how do we get the corresponding weight? Yeah, we solve for it. Okay, we say z is equal to y minus mu over sigma. And so here we've got an equation, we've got one unknown. So I plug in the values that I do know. Z is equal to negative 0.25. I don't know why, that's the value I'm searching for. Mu is 1600, sigma is 150. So we're looking for the value of y. We solve for it, multiply both sides by 150. What is this? 37.5. Is equal to y minus 1600, so we get y is equal to 1562.5. Is that right? Alright, is this okay? Yes, okay. Another example, or are we comfortable moving on? Do one more. Okay, sure. Alright, we'll change this up. I don't know. What could possibly else? What else follows that? Alright. Weight of a black bear. I always like putting Google to the test. Alright, what do you guys think? The average weight of a... What? This is completely useless. Alright, weight of a black bear. In kilos or pounds? Yeah, I mean, it doesn't matter. I mean, any guesses? Huh? 1,000 pounds? It says anywhere from 130 to 660 pounds. That's a huge, huge range. But I mean, I guess technically humans can also fall in that range as well. But 130 to 660, I was not expecting to have such a massive thing. All right, we'll just say 400. Who knows? Okay, so we'll say for black bears. How many kinds of bears are there anyway? This reminds me of. Did anyone watch The Office when it was on? Yeah. Okay. So we'll just 80 because there's so much variation, right? Okay. So we'll say the mean is 400 pounds with a standard deviation of 80. Okay. All right. So I'm going to ask. What is the weight of a bear in the 90th percentile? No, that's for male black bears. Female black bears weigh between 90 and 175 pounds. That's like way smaller.
You have a 90 pound.
Huh?
You have a 90-pound bear with a 600-pound bear.
Yeah, yeah. I guess they make it work somehow.
That's weird.
Can I ask you something about that one? So what if you, based on your answer from that question, what if you want to find the weight of a male giraffe in the 60th percentile? How can you figure that out with that answer?
Well, you still have to figure out your z-score, and I mean, if you understand the symmetric-ness of the distribution, you know that the 60th percentile would have a z of positive 0.25.
Okay.
But if you didn't, you'd just look it up, and you'd get z equal to positive 0.25, and then you'd go from there.
Okay.
Okay? But yeah, there's no quick way.
Okay.
There's no quick
Just not
thing to do. Okay. £90 bear, I feel like you could fight that and survive. We don't encounter very much wildlife in Southern California, or I should say in Los Angeles County. Mountain lions, maybe. God, look at weight of a mountain lion. All right, what did we get? 502. Yeah, that's right about what I got. Okay, so 90th percentile, we have to figure out the z-score. And what do we get for a z-score? 1.28. So we are looking up, 90th percentile, and the closest number we find is 0.8997, and that's in the row 1.2 on the column 0.08, so our z-score is positive 1.28. Okay, as it should be, because 90th percentile, we're over the halfway mark, so we should be positive. So plugging that in, solving for y minus mu over sigma, we have 1.28 is equal to y minus 400 over 80. We do 80 times 1.28 plus 400 is equal to y, and we get 502-ish. Okay. .4, is that the exact value? Okay. All right, are we good there? We're good? Okay. Then, okay, so there is a section in the book called Assessing Normality. And that is about, let's say you suspect your data comes from the normal distribution, and you want to know, does it actually come from the normal distribution? Well, we use something called a quantile plot. And I have a few exercises in the homework which really, probably go more in depth than I even care to do, okay? Basically, you do something called a QQ or quantile plot. And if the data comes from the distribution that you are expecting, in this case a normal distribution, your data points, when graphed on the QQ plot, will go in something that looks like a straight line. If your data, when you graph it in a QQ plot, does not go in a straight line, okay, you get something like this. Okay, so generally in a QQ plot, the middle points or points near the middle line up, but then points in the ends don't. Okay, you have something, this would be not normal. Probably heavy-tailed. And then maybe your data goes like this. Okay, also not normal. The short of it is that straight line, well, straight line means your data matches the distribution that you're testing, okay? So we would call this a QQ normal, and you could use it for a QQ, whatever other distribution you have. QQ Poisson, QQ exponential. There's other distributions that exist that we're not going to bother learning in this class because the normal is the most common and the most important one for our course. Others exist that are important but are less common, so we're not going to bother with them. So you have QQ plots, and basically if the data goes in a straight line, it fits the distribution you're looking for. So if you made a QQ normal plot and it looks like this, your data is normal. And if it goes like this or like this, your data is not normal. Okay. You have questions that kind of ask for more detail than that, but it should be okay. Hang on, I'm getting a little alert here that I should read. Okay, everything's fine. Okay. So let's go back to that thing I said at the beginning of the class, going over the binomial distribution. Okay. Well, actually, before I do that, are we feeling okay with the normal distribution of the problems we've covered so far? Okay. So at the beginning of the class, we talked about the binomial distribution, and I said, maybe we have an example where I say I'm going to take 20 seashells. And I want to know what's the probability of getting between 50% and 80% striped shells. Okay, and we said, well, in order to answer that question, I would have to do 20 choose 10 plus 20 choose 11 plus 20 choose 12, all the way up to 20 choose 16. Do you guys remember this? Okay, so that would be the way to answer that question. But I said that's rather tedious. Okay. So we have some methods to kind of approximate the normal distribution. I mean, not the normal distribution. Approximate the binomial distribution with the normal distribution. Okay. Now I have to, I don't know, say a disclaimer and say, in this class we're learning a lot of methods to do calculations by hand, for better or worse. That's the nature of learning classical statistics. We're learning to do these things by hand. Most modern statistics and even probability is done by computer these days. And so, you know, some of these methods, even for approximating, kind of become less useful because we can have a computer calculate the exact quantities very quickly. Whereas to do it by hand, it would be very tedious, and that's why we want these approximating methods. But having a computer available almost defeats these things. But I think there's still merit in learning them, okay? So I'm just going to say that. Okay, so when we have the binomial distribution, okay, when n times p and n times 1 minus p are both 10 or greater, the binomial distribution looks very similar to the normal distribution. Okay. Okay, well we have the normal distribution looking something like this. Okay. And that looks a lot like the normal distribution. Okay, so the binomial distribution, it's discrete, but the shape ends up looking unimodal and symmetric, and looks very much like the normal distribution. Okay. So, in the binomial distribution, you are given n and p somewhere in the statement of the problem, and you're looking for the probability of j successes. In the normal distribution, you need a mean and a standard deviation. Okay, so binomial has n and p, and the normal needs a mean and standard deviation. Okay. So to relate the binomial to the normal, we are going to use the mean equal to n times p. Okay. So the mean of the binomial distribution is n times p, and we're going to use that as the mean of our normal distribution. Okay. And the standard deviation is going to be n times p times 1 minus p square root. Okay, so the standard deviation of the binomial will stand in for the standard deviation of our normal distribution. And this allows us to answer questions where it would be too tedious to answer with the binomial. Okay. So just imagine I said, I don't know, 60% of shells are streaked. Okay, and let's say I'm going to take a random sample of 100 shells. ask, what is the probability that between 50 and 70 shells inclusive are streaked, or striped? What did I say? Streaked. Okay. So with binomial, we would have to do 100 choose 50, something, 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 plus 100 choose 51, something, 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 plus all the way up to 100 choose 70, something, something, something. 0.6 to the 70, 0.4 to the 30. That's a lot of numbers to add up. We don't want to do that. Okay? So we're going to do the normal approximation instead. Okay? We're going to say the mean is equal to n times p. So that is 60, 100 times 0.6. And the standard deviation is going to be the square root of n times p times 1 minus p. 0.6 times 0.4, I get the square root of 24, which is very close to 5, but not exactly. What is it? 4.87? 4.899, so 4.9. That's good enough. Good enough for me. So what I have here is I've got kind of a normal model, and I'm basically going to go down from 50 up to 70. Okay, and so and I have mu is equal to 60 and sigma equal to 4.9. There's one thing that we have to account for, and we can't just dive in and use 50 and 70. Okay, we have to do something called a continuity correction, right? And so just imagine I have, the binomial model has these bars. Okay, and the bars, let's say, are centered at these at their numbers, okay? So this is the bar centered at 49, bar centered at 50, bar centered at 51, obviously not to scale. This bar is 69 and this bar is centered at 71. If I shade just from 50 to 70, I would be missing half of this bar. Can you guys see that? And if I shade all the way up to 70, I would also be missing half of the bar centered at 70. So where I should be drawing my cutoff is actually down at 49.5 over here, and where over here? 70.5. Okay? So with the continuity correction, I'm going to draw a cutoff at 70.5. And over here, I'm drawing a cutoff at 49.5. Okay? So you always have to ask, do I want to include this bar? Okay? And because I'm saying between 50 and 70 shells inclusive, that means I want to include the bar for 50, and I want to include the bar for 70. Okay? So if you draw a bar centered at the number, and you shade it in, then it should clue you in and say, okay, I'm going to draw my cutoff at 49.5 and at 70.5. Okay? So you're always going to be going plus or minus 1/2 or 0.5, but it depends. There's not like an easy, hard, fast rule as what to do. It requires careful reading of the problem, kind of visualizing the bar there, and deciding whether you're going to go above or below. Okay? If this problem was written, what is the probability that between 50 and 70 shells exclusive are streaked? So that means basically between 51 and 69, not including 50, not including 70, where would I draw my cutoffs then? Yeah, I don't want to include this bar then, and I would draw my cutoff at 50.5 and at 69.5. Is that okay? Everyone?
I have a question.
Yes.
So is that 0.5 like an actual accurate amount, or is that just compensated?
So it's a compensation, okay? Remember, this is an approximation to begin with, okay? We're not actually going through the binomial calculations. If we needed an accurate answer, we should be doing this tedious binomial calculation. What we're trying to do is we're trying to get an approximate answer using the normal model, knowing that the normal model is pretty close to the binomial model, okay? And the approximation is actually very good, especially if you take into account this continuity correction. Okay? So here I would have two z-scores to calculate. I would do z is equal to 49.5 minus 60 divided by 4.9, 10.5 over 4.9, or negative 10.5 over 4.9. And I get negative 2.14. And on the other hand, 70.5 minus 60 over 4.9. And I would get positive 2.14. Okay. I would look this up in the z table. Okay. So I look up negative 2.14, and the area to the left, giving me an area to the left of negative 2.14 is 0.0162. And over here, the area to the left is going to be 0.9838. Okay, so the area between what I want would be 0.9838 minus 0.0162, and I would get 0.9676. Okay. So what is the probability that between 50 and 70 shells inclusive are streaked? 96.76%, okay, so about 97%. Okay, again, this is an approximation using the normal model. We could do the binomial calculations and we would get the exact answer. This is our approximation here. And that makes sense. If 60% of shells are streaked and you're going to pick 100 of them, you would expect that in your batch of 100, you're going to get something between 50 and 70 streaked shells. Maybe something outside of that, maybe not. But that's what we would have. Is that okay? Yes, question?
We do this continuity correction when we're looking at a binomial model that has n times p and n times 1 minus p greater than or equal to 10?
Yes. Okay. So yes, the important thing about this continuity correction, the continuity correction only comes into play when you are approximating the binomial with the normal distribution. Okay? If you're just using the normal distribution by itself, So like when we were doing the weights of the giraffes and all of that stuff, don't be adding plus or minus 0.5, okay? There's no sense in that. That's just the normal model. You're going to use the normal model, okay? The only reason why we're doing plus or minus 1/2 here is because we're trying to approximate a discrete thing with a continuous thing. The binomial is discrete, the normal model is continuous, so we have to account for this like imaginary bar that's like being cut in half, okay? So with the normal model, don't be adding plus or minus 1/2. If you're doing the binomial by itself, don't add plus or minus 1/2. The only time you're going to add plus or minus 1/2 is when you're approximating the binomial with the normal model, okay? Yes?
But it's not always the case that you have the bar divided in the middle or whatever, right? You can have it right at the edge also. I mean, I guess the chances are low, but...
Okay. No. Yeah, when we are doing the normal approximation to the binomial, the bars, these bars, this is just kind of an illustrative tool, will always be centered at the number. And so we are always cutting them in half, and we're adding 1/2 or subtracting 1/2. Okay? I think you're thinking of like a histogram or something like that. Then yes, that's the case. But we're not doing that. This is specifically for this situation of approximating the binomial with the normal. Okay. In the book, it talks about dealing with a situation where instead of counts, you're dealing with a percentage. Okay. So I could rephrase this question. If I'm taking a random sample of 100 shells, I could ask, what's the probability that between 50% and 70% of my sample is streaked? Okay, that's asking the exact same question. And my recommendation, so the book provides another set of formulas when you're dealing with percentages. I find that that extra set of formulas just confuses students, and it actually gets really messy when trying to do the continuity correction. So my recommendation is, if you're given percentages, ask questions about percentages, turn them into counts, okay? So if the question says you're taking a sample of 300 shells, and what's the probability that 50% of the shells are streaked, in your head you should say, well, 50% of 300 is 150 shells. Okay, so turn it into a count and deal with the counts. The counts are always going to be easier to deal with when you're using the binomial and trying to approximate it with the normal. Okay. But yes, there are like another set of formulas in there. Don't. If you like them, you can use them. But my recommendation is just use the ones for the counts that I gave you here, and deal with them that way. Okay. So I wanted to do. Oh, yes, questions.
I have to be very clear about one thing.
Yes.
Just, we use the normal curve to approximate the binomial curve of
Yes.
the model.
Yes.
When n times p is greater than or equal to 10, and when n times 1 minus p is greater than or equal to 10, that's it.
Yes. Yeah. Okay. Yes. So yes, we can use the normal curve to approximate the binomial distribution when n times p is greater than or equal to 10, and n times lowercase n times 1 minus p is also greater than or equal to 10. Okay. Some textbooks will say 5, and that's also okay. The thing is the binomial distribution, it's made up of bars, okay? It's discrete. And at some point, the difference between a bunch of bars and a smooth curve gets really small, okay? And when n times p is, a lot less than 10, like say 3 or 4, the difference between the bars and the smooth curve can be significant. And so the approximation just gets worse and worse, okay? Obviously, you know, technically one coin flip is still a binomial situation, and trying to approximate one coin flip with a smooth, continuous curve is not going to do a good job, okay? So anyway.
Is there a point in which like the NP is so large that we don't have to do the 0.5?
I would say yeah, but I guess you'll always just have to be aware that the answer you're getting, if you're not doing the plus or minus 0.5, you're always going to be cutting off just a tiny bit. You know, you're always going to, your answer is going to be a slightly bit smaller than what it actually is. Okay, just be aware of that. Okay, so I wanted to do a demo on the computer of using R in RStudio, but I forgot to bring my computer, so it's not going to work. All right, so